Penn State University with PlantVillage. And today, our data scientist at the team, Derek Moore, co-developed the materials with me. I think he has some technical issues, so hopefully he will join us soon. So today the topic is about land cover classifications using satellite data. By land cover classifications, I mean land use type, just like the urban or the crop or the forest, even the grass or the shrub. I will go through this with you together later. So first, I want to take a brief introduction on the team I work with, the PlantVillage. Here is our link. So PlantVillage is a public good based at Penn State University, main campus in the State College. So our goal is to actually help African smallholder farmers to achieve food security and solve different biotic and abiotic stressors. So kind of within our team, we are taking different approaches. We have our AI system, which is also a mobile app called Nuru. It's actually means light in Kenya. So which can help the farmers to diagnose what disease their plant are having in the field, and it's perfectly work offline. And we have drones to do the scouting, and also we use a lot of like front-end data science and machine learning, remote sensing techniques. So our team is pretty large, up to, I guess, 100 people. We have our IT architect, we have agriculture extensions, we have Dream Team, which are based in Kenya and work on the ground and work directly with farmers. And we have Android engineer and developers. We're actually all over the world. We have people in Kenya, people in Russia, and all over the US, actually. We're all based in different locations. So I'm currently based in New Hampshire. Then here is the today's topic. I'm sure kind of everyone is somehow familiar with the satellite data. It's actually the data at high spatial resolutions. They can be used for land cover classifications. Just like Google Pictures, you can actually see this is a farmland and this is a urban from the Google images. And also they can use the full vegetation monitoring, especially associated with the agricultural sector I'm working with. If you plot out the data within different period, you have a time series images, you may see the growing cycle of your vegetations, and you may also estimate, how much crop yield you have just based on some parameters you extract from the satellite data. So the science behind it is pretty simple. So different land surfaces reflect different radiations and have different, so when you collect a broad range of spectrum, you can actually identify what is going on the ground. So here I'm listing two popular open access satellite data. One is Sentinel-2 data, which will be used in today's workshop. And another is Landsat-8 data, which is also popular, but we didn't use it today for some reasons I will talk about right now. So the Sentinel-2 is actually developed or operated by the European Space Agency. It has, it measures like 13 bands, different spectrum bands. They are visible, near infrared, and shortwave spectrum. And so kind of the satellite revisit every 10 days. So you will have a whole new set of image of the Earth for every 10 days. And the spatial resolution, depending on which band, is 10 meter, 20 meter, and 16 meter. But you can always, downsample the 20 meter and the 16 meter resolution to 10 meter resolution. And it's free and open access. So Landsat 8 data is developed by US Geological Survey. It collects 11 bands, and it revisits about twice per month, and which means every 15 days you get a whole set of new images of the Earth. They are free and also open accessible. And they have, you can download those images from their, official website if you register, which is free. But here I'm not going to go into their official website. Instead, I'm going to use the Google Earth Engine to extract satellite data and run the land classification models. It's kind of a pretty popular used topic. Here is an example tutorials, which is literally using the Google Earth Engine called platform to develop to extract the information and develop the simple models. A kind of a benefit of this is users do not have to download those huge satellite data to their own personal computer. Because we can imagine, first of all, the Earth's surface is super large. So actually, the system divided the whole Earth image into different tiles, which is squares, and for each tile, for each like square, you may have like 11 to 13 geotiffs, and which is corresponding to different bands, and each geotiff can be gigabits, tens or almost close to 100 gigabits. So you can imagine how can you process those huge amount of image data, geotiff data in your own PC. And then that's why you can actually see the image and extract the information from the Google Earth Engine. And I played with it. It's kind of faster processing time. So here is the Google Earth Engine like window. But here we can also visit the Google Earth Engine through Python. There is a package called Earth Engine package EE. The benefits of using Python is because the Google Earth Engine JavaScript code editor has some limitations in, for example, if you want to run some really front end or fancier machine learning models, and which definitely more convenient if you do this in Python, because it has a lot of built-in packages like scikit-learn in there. And also, you may want to process or pre-process or post-process your data. And that's why we're using Python today to do this job. So kind of the goal of today's workshop is land cover classification using Sentinel-2 data. So our data set is 900 survey records with latitude, longitude, which give us the geolocation and the survey date and the land cover labels. This data set is actually originally served totally different purposes. This data set is when we we are dealing with the locust invasion problem back to 2020. If you heard about this, in 2020 there are a lot of rains in the East Africa, and then which kind of triggered a huge desert locust crisis. So locusts originally only exist in desert area because they are desert locusts. But now, because of rainfall and the vegetation, so they kind of moving out of the desert and then move towards like forest, shrubs, and the crops, which cause a lot of damage. So that's what the data set is about. And then we will also collect the Sentinel-2 data, which is 11 bands and another NDVI index, which I will talk about later, to those survey points. And then the Then the third is train and test XGBoost multi-classifiers to predict land cover. So for those of you who doesn't know XGBoost model that much, so XGBoost model is essentially ensembled tree models. So it's kind of a group of a lot of decision trees, kind of like random forest, but it has a gradient training like training procedures. For the interest of time, I will not explain explicitly how the model works, but more showing you how to use it in Python. And then again, the purpose is more like go through this process and show you the power of the centralized data and how to input this into a model. Because of training the model, collecting the data may take a lot of times. So our goal is now to train a model which has highest accuracy as possible, because that will take us a long time. And plus our sample size is really small. We originally have hundreds of thousands records, but I only picked 900 for the interest of time. And in the bonus part, I will show you a quick demo on how to extract time series Sentinel-2 data to the point of interest. So if one day you want to run a time series model, just like, for example, like some deep learning model, I can show you how to collect the data in case you need. So that is the introduction of the workshop. I will now move to my Jupyter notebook. I will stop sharing and switch to my Jupyter notebook. 1 second. If you are following, that should be the Jupyter notebook you are looking at. So that's the package I'm talking about. If you have trouble to import these packages, probably because you didn't install it first, I will just like pause a second. Yeah, Chris posted the I will just wait here for a couple of minutes until everyone, like not everyone, just like until some of you can import the EE package. If you don't have GeoPandas, probably you forgot to install them. Yeah, Chris is supposed. In the worst case, if you couldn't get this imported, it's also fun because for the interest of time, we are going to use preloaded data. But if you have it, it's better to show how this package works. But if you don't have it, I kind of extract the data prior to this workshop, and you can just directly load the data from a CSV I shared. Okay, here I'm going to show what will happen if you do this import and then do this authenticate and initialize. So if you do this, it will it will give you a link to ask for your it will give you a link. You can copy this link to your browser, and I think what happened to me is just a window just pop up and ask for my permission to visit it. I will. I will just stop share because that has messed up my confidential code. And okay, I may just continue to share. And then it will ask your permission to access your Google account. Most time you just click allow, and then they give you a code, and you copy and paste it to the to your Jupyter notebook and hit enter. And then they will say successfully save the token. Has anyone succeeded so far? Can I move on? Again, this is not mandatory. Yeah, if you, I can move on. Okay. Okay, then I will just move on. Please let me know if you want me to pause.
Yeah, go ahead, Fei.
Okay. Okay. So first I will load the land classification data. Yeah, if you put all the files that in the GitHub in the same parent folder, you should run this without problem. So that's the location we surveyed, and that's the date we surveyed, and then that's the land cover classification of that point. And then first of all, we want to change the date column to actually a date object. Here you can see from the Excel CSV is just like the string format. So we use the panda datetime index function. Now it's in the datetime, and then we want to know. So here is our y variable, which is our dependent variables. We want to predict this LCC in the model. So we first want to have a count of the LCC values. So here we have 3 classes. Here we have like three classes: urban, forest, and agriculture, which is cropland. And for each classes, we have 300 records. Again, because that is what I selected from a much larger data set, and I intentionally pick these 3. Pick these 3 classifications and make sure we have a balanced class. Sorry, I see the in the chat someone. Yeah, someone posted images as authorization errors. Yeah, that is probably because you didn't sign up for the Earth engine. If you can quickly sign up, I think you should be good to go. Okay, back to my Jupyter notebook. And then, and this data is actually from Kenya, all from Kenya. So next, I want to show how the data looks like in the country of Kenya. So first, I will. Yeah, first I will read the shapefile of the Kenya, actually of the Kenya counties as a GeoPanda data frame, and then I will plot. And then I will also transfer my LCC data to GeoPanda data frame by giving it a geometry column, which is a point. Yeah, definitely, obviously it's a point. And then I can plot. I can plot the points on top of the Kenya map. So it's not the data itself. It's not uniformly distributed in Kenya, which makes sense because some areas has more people living in residence, and some areas, because again, people originally report their locations because there is a locust. They want to report, their farm or their land was damaged by the pest locust. So we can see maybe some crop areas or farmland where people live has more reports, and also where so we can see it's not evenly distributed. And then next step is kind of the key of the workshop. How can we extract the Sentinel-2 bands values to points? In case you wonder what are those bands, here is a Wikipedia page to tell you what each bands are and what is their bandwidth and wavelength. So for example, if you want to focus on recognizing cropland or vegetation from the Landsat image, you may want to focus on band 5, 6, 7, and depending on your purposes, you may want to focus on different bands. But here, but here, to kind of make the full usage of this data, we just extract every band values that we can have. So first, again, like I said, this Sentinel-2 data update is updated every 10 days. So for example, let's see, for example, if you have a survey data at April 7th this year, and it is highly likely to happen is in that date, you don't have a refresh, you don't have an image that was taken in April 7th. And so you may want to say, okay, if I don't have an image taken in April 7th, then maybe April 1st is also good because they are very close. So I don't expect the land surface to change dramatically. Or if I don't have at 7th, maybe April 17th is also fine because it's only 10 days away. And another issue we have to consider is when the satellite are taking pictures, one important criteria to see whether it's a good picture or not, it's the cloud cover. So if you don't have a clear sky that day, there are a lot of cloud cover. Mostly you will end up having an image of cloud. You couldn't see anything, under the cloud. So even though you really have a picture taken exactly in April 7th, you may don't want to use it because it has a lot of cloud covered. So you may want some clearer, low cloud covered image from a nearby date. That's why in the extraction code, the first thing I did is to create 2 data columns to define the date period of the Sentinel-2 images. So kind of here, what I did is I do 16 days before the survey date and 16 days after the 13 days. So I give it like a 1 month, relatively 1 month period, which may cover like 3 images. And I will say, look into these 3 images, which were taken around the same date as the survey date, and then give me and then pick the best one, which has the least crowd covered one. So here I'm using the Panda to time delta function to define my data range, data minimum and data maximum, which is like a 1 month period near the survey date. And here is a function on how to extract the data to the point of our interest. So first we want to define, just like I said, this Sentinel-2 data measures more than 10 bands, and we want all of them. Why not use all the information that we have? So this is the band values we want, and this is lat and long geocoordinates of your point of the interest, and I just change it to a point geometry. And then the next thing I do is select images, select the image I want based on the following criteria. First, like I said, this image has to be within the data range we defined. Like between filter date, it must be between the data minimum and the data maximum. And then I want to sort these images by cloud cover percentage. And then I want the least cloud covered images. And another very important thing is I want the image, just like you said, just like I said before, they have the images of all over the planet, the Earth, and then they divided this whole Earth surface in different tiles, which is different squares, different pixels, and I want the pixel which contains my point of interest, which definitely makes sense. Makes sense. Then based on those materials, those criteria, I pick up the image which has the least cloud cover, which contains my point of interest. Should be interest. My point of interest, and was taken in the data range that I defined. And the next one, and then the next command is to attract values from the above image to the point of interest. So this image select sample regions is the function we call. So image select, we select all the bands like I defined before. So in your future use, I may talk about later. If you only focus on vegetation, you may only need B4 and B8. I will talk about this later. So you don't need like all these 10 different bands. You may only need one of them or two of them. And then my collection is P, which is the point I defined. And the scale means resolution. If you still remember, there are 10, 20, and 16 meter resolution, and I want the finest resolution. And then next I will show better by examples. So what I got in the end is a very nested, complex Python dictionary objective. And what I do here is actually to extract those band values from those dictionary. And this is defined, and I will show what it's doing with an example. I will just write. And then just like I said, don't run this command for the interest of time. So so theoretically, we should apply this this function to each row of this data frame. So data frame apply this function and each row, which means for each of the records I run of this function. But you can still imagine I do this, filter images and image extractions. They may take a long time. So for the interest of time, I already did this step. And then you don't need to write it. You can read directly from my preload data. So I will just skip this. And then this is an example. For example, I only run like this function to 2 rows in my data frame to let you know what is happening here. So I ran this for the row 3 and row 4. So in the end, what you directly have is this very complex and nested dictionary, we have the dictionary key type is a feature collection. We have columns, and we have properties, which tells us band order is 11, 12, etc. And properties. Yeah, so if you see these properties, the value after properties is what we need. But actually the values of this property keyword is another dictionary. If you see the logic here, in the other dictionary, we have, kind of a second level of properties, which tells us the band order, the features, the geometry. The geometry tells us the coordinates of the points we just did. And finally here, we got this, third level of property, which give us the value of the values of each band, which is exactly we want to extract here. So you can see in the end, this dictionary, this function return us a list of dictionaries which contains the band values. And so this is this function is doing. And then back to the monitoring codes. So again, for the interest of time, we just use the catch data for the data for dataset. So you can run this cell. And then originally this is what I put in my GitHub. In my GitHub, you can see this is all the band values we extract, and this is the LCC, light and long, and the survey date. And then we just need to do a little bit of pre-processing before we input them into our XGBoost model. So the first thing I did is to drop off this light and long and date columns, which is not a dependent variable or predictors in the model. So I dropped these 3 columns off, and then I add another column which called NDVI. NDVI means normalize the difference vegetation index. So it is a vegetation index. It's kind of an assessment of how much living green you have on your ground. So that's an indication of how much vegetation you have. For example, if you which is very important for us because we have urban, forest, and cropland land classifications, and the vegetation index is definitely going to be able to differentiate between those 3. So I do the vegetation index calculation again. The equation is pretty simple. It's just B8 minus B4 divided by the sum of B8 and B4. That's why I mentioned is a lot of people only interested in NDVI. So you only need to extract 2 band values actually. If that's your case, you don't need to extract all these 11 band values. And then next, I kind of convert those string or text type of LCC code to like integers. Because our XGBoost model only take integers as dependent variables. It cannot work with the string or text as your variable values. And so here is actually our cleaned data set. We are predicting the LCC using all other columns. And then finally, we are into our XGBoost model. And then first, I think it's pretty standard to split a train test data set. Actually, to be more robust or a more popular way to do this is actually to have a trained text and a validation data set. But so you have a completely hold off data set. I didn't do this because our data set is really not that big. We only have 900. We only have like 900 records, and that's why I only split it into train and test. I will talk about later in the code where you can use a validation data set. So kind of our X, which is our predictors, is all columns except the LCC column, and the LCC column is our Y variables, which is our dependent variables. And then this is a label encoder. Kind of a it kind of does what this command does, but if you don't do this again to kind of transform your label encoder of your Y, this function doesn't work. So I'll just do the feed transform here. And now I can split my data set YX, and text size means I hold off 20% of my whole data set as my test data set. And if I give it a random state, which means if I run this command again, it will not randomly split it in another way. It will split it as what I ran it in the first time. So this is optional. So I will just go ahead and run this. And then next is our kind of complex part, but it's kind of complex part, but it's actually not that complex. So I will define some parameters in my XGBoost model, and I will also define a searching grid. So like which parameters I want to tune, and what is the searching grid of the parameters that I tune. So if I can, yeah. So my estimator, I want to first define or actually boost the classifiers. Some key parameters here is first the objective. I choose like multi. That is because it's a multi classifiers. If you have a binary classifiers, it will be the binary. But actually, if you put a binary in here, it will also works. Because if you put a binary here, the XGBoost model will just treat, class 0 versus non-0, class 1 versus none versus not 1, class 2 versus not 2. So it will kind of interpret your multi-classifiers into several different binary classifiers. And kind of this tree method is the I choose histogram because it's kind of it's faster, and then this seed and then this end thread just mean I want to use all the processing cores in my computer. And here and then this is about the classifiers, and then this is about I'm using a repeat stratified K4 searching grid. I think everyone knows what is a K4 the cross validation, which means for example, if you have like 10 for it just means it divided your data set into 10 sub data set, and it will using one as validated data set, and then the rest of 9 as testing data set. And then kind of for the repeat is like it is redo it by n times that you defined. Kind of here I'm seeing I'm split this data set into 3 proportion into 3 data set, and I want to repeat it twice. But actually this 3 and 2 is a very, very small number. Usually you want to do a 5, repeat it like 5 or 10. I choose 3 or 2, which is really not that powerful. It's only because obviously, if you increase the numbers, you need to repeat, you take a longer running time. And today I don't want to waste everyone's time on waiting the model to run. So I choose like 3 and 2, which is really not powerful numbers here. Usually people do 5 or 10 or even larger. And then here is the parameters that I want to tune, which are all the parameters used in the XGBoost model. They are pretty standard, parameters in any tree models. In any tree models, for example, the maximum depth is the maximum depth of your tree. If you have like two small depths, of course, your model will not be accurate. If you have too deep of the trees, your model may have overfitting issues. And the N estimators is the number of the trees you want, and the learning rate is to go to the next iterations, how much steps you want to move forward again. And then, and there are all other different kinds of parameters you can tune. And then, and estimators, you can probably do a 50 to 200, and the step is 10. But I didn't do like very fine tuning again because of the timing issue. That's why I just show you the process, and you can fine tune your own models later. And then the fit models, the fit parameters is actually I have like 2 here. The early stopping round is 10, which means if I go 10 rounds of iteration, but my loss function is not decreasing, I will stop training. That's also save time and also prevent overfitting issues. And my evaluation set is actually X test and Y test. Kind of that's why I said, theoretically it would be better if I have another X validation or Y validation data set, which is completely hold off, and the model is completely strange to the model when I do when I actually evaluate the model as the performance. But here again, due to the smaller data set, I didn't do this. But if you have a larger data set, you can split the data set into 3 proportions, and you can use X validate and Y validate here instead of X test and Y test here. And kind of the evaluation function I'm using here is called a Mathieu correlation coefficient. It's actually works better for the binary classifiers, but I want to use it here kind of because I want to introduce you these new parameters that are maybe not very commonly used. Let me share what this one is doing. Wait. Okay. 1 second. Kind of this is a Mathieu correlation coefficient. I like this. It's actually Derek recommended that to me. I like it because it's actually calculating a coefficient, which this is a typical confusion matrix for the binary classifiers, but it's actually using the values in all these four cells. And okay, here is the equation of that. So I will not repeat that. But compare with accuracy, which may compare with accuracy and other like parameters, you can consider this one as well, because using all elements in those confusion matrix. So that's why I kind of burned it up here. And then I run this, and then I will start feed the model. That should be running super fast, like 1 or 2 minutes. maybe 1 minute. Okay. Okay, it's done. So let's see the best parameters we found. So here is our tuning results. We have the best combination of learning rate, maximum depth, and n estimators, which is the number of the trees. And just to follow the tradition, let's see the accuracy. The accuracy about 0.47, which is not that good, but just like I said, it's more like a process and learning. Instead of really get the best model or get best performance, and here is a plot confusion matrix functions we can use to plot our model's performance. So we have true labels in the y-axis. We have predicted labels in the x-axis. Kind of here we can more or less see the model performance. When the cropland is doing okay, most of the cropland was predicted as cropland, but we got some confusion with the forest, which makes sense. They are all vegetations, and our urban is the performance of predicting urban is doing the best. Urban seldomly got confused with cropland and forest, which makes a lot of sense. But for our forest, again, forest and cropland was mistaken was confused the model a lot. So that is something. That is something we can consider. And then again, and next we can see our feature importance. This is the function to get the feature importance, and I just do a simple bar plot to it. Okay, that makes sense. Like I said, yes. Okay, I see. I see a question in the chat. Yes, the LCC is the label in the data set. It stands for land cover classification. Okay, back to the code. So like I said, NDVI is really a powerful tool to differentiate vegetation from non-vegetation. And then this is the main part of today's seminar. And then we have a bonus on how to extract a time series Sentinel-2 data to points. I think that is good techniques or good next steps. Like we said, we had trouble differentiating cropland with forest. Maybe they are green. Their greenness and the vegetation index may very similar to each other. And then how can we differentiate each other? So, and then one way to do this is to see the time series Sentinel-2 data. Just like I said, if I go back to my data label, this is, for example, this is my first records. We have labeled LCC. Yeah, LCC is the label, is a Y dependent variable we want to predict. We have LCC, and for each records, it is corresponding to one location, which is fine, and one date. One date means the survey date of April 7. But what really happens, and then the next one is forest. The survey was taken in last year July. But what likely happened is this physical point in Kenya is cropland. It is very unlikely that it will change to a forest next month. For example, you went to this place in April and it's a cropland, and the next month you visited, it becomes a forest. This very, very unlikely to happen, because if you have a farmland, you probably want to farm it for 10 years or tens of years, decades. And again, for this, forest, it is the same. If you see a tree, a forest in this point in last July, it is very unlikely to say, 3 months later, this large forest was gone to urban or to agriculture. And then based on this theory, and also we know that one time point of, for example, NDVI or band values is really hard to differentiate these two. You may want to see how you may want to collect a time series of these band values. For example, for 1 year, and then compare this with a time series values of this point, for example, in 1 year. If you compare time series data to see really how this NDVI changed over time, maybe a better strategy to differentiate forest, for example, with from cropland. Because for the cropland, you may harvest data. For example, in some months of the year, you found the NDVI or vegetation index largely dropped all of a sudden, only because human remove the crop, harvest the crop from the ground. But in the contradictory, for the forest, it's likely that it will remain green, very green throughout the whole year, because no one is harvesting the forest, and it's in tropical areas. So kind of based on this assumption, I kind of want to show how to extract time series band values, how to extract the time series band values to the point of our interest. And okay, so here is a kind of advanced version of the function of the previous function. So first, we have lat and long, and then define the point of our interest using the latitude and longitude. And then again, I want to create an image collection within 6 months of Sentinel-2 image data, one for each month. So kind of what I did first here is I want a date list. Probably I can do a quick. Okay, probably I can just print. I can do a print here, just to show you. Yes. Okay, I may just run this very quick first, and I think with the examples, we may have better idea. So to do this, first I get a very small subset of the entire data set, because just to show you how this one works. So I have a subset of data frame which only contains lat and long and date with five rows, and I will run this quick, and then yeah. So yeah, here is what I'm doing. So the first record is the survey date, and it's a survey date, and I want to create a 6-month period around this survey date. So 3 months before the survey date, and then the 3 months after the survey date. So in the end, I have like six like data period, from 2020 to from January to February. I want so from January to February, and I want to gather Sentinel-2 data during this month, and another time point is February to March, and March to April, April to May, and May to June, and June to July. So this is the data. So this is the data. This is the data list I want, and for each of the data interval, again, I want to pick up the images, which means I want 1 images between the January and February, which has the least crowd cover and contains my point of interest. And I want another image between February and March, and have the least crowd cover and also contains my point of interest. And I want the third image between these two data period, and etc. So in the end, based on this data, I can have 6 images, which is in a time order. And I want to extract the values from the image collections, which is actually 6 images. If you want, you can do a whole. I have 6 months. You can do a whole year, and then again, I can extract the values from this image collection to my point of interest. And let me just comment this out and to see what is this one is doing. Yeah. So again, just like I said, this is the time series band value associated with my first point. I have 6 months, and in each month, this is the band values. And this is my second point. This is my third point. This is my fourth point. This is my fifth point. So, originally, for each records, I only have 1 row, which is a single time point. But with this time series functions, for each point, I have like 6 rows, which is the time series data. And then, for example, if with image collection, I will take questions now. With image collection, are you basically for each of the days? Yeah. Yes. Yes. With image collection. Yeah. Yes. With image collection, are you basically getting images for each of the days specified? Yes. Yes. Correct. Yes. With image collection, I may do this. This may be better. Yes. So yes. This is what I did. So this is from the image between those first 2 days. And the second row is from the image between the February and March. And then the third row is the image between March and April. So fast and so on. So I have like 6 data period, maximum date, a minimum date, a maximum date. Yeah, so with image collection, I'm getting the images for each of the
Fei,
data.
when you say you have the time period between those you're collecting, right? So
Yes.
does it pick up any random date in between and get the image for you for those dates, or how does that work? Just curious.
Okay. So like I said, we have like images for every 10 days. So probably between those 2 days, I actually the Sentinel whole data set may have like 3 images because the Sentinel took pictures every 10 days. And yes, and again, I use the crowd cover. I said, okay, I know there may be several images between these first 2 days, but I want the images with the least crowd cover, which is the most clear sky. And I said, okay, this will be my image, and I put it in my image collection. And then I move to the second date interval, which is February to March. I will say, okay, let's look into all the images, which is probably 3 between those 2 days. And again, I want the images with least crowd cover. And then I pick my second image and I put it in my image collection. Am I clear? Am I answering your question?
Yes, yes, thank you. That was very clear.
Oh, another question is, would a CNN tail-based approach based on the RGB bands fast with the NDVI scaler work better for the accuracy? I think, yeah, I think maybe a kind of a deep learning model, narrow work model may work better, but may work better than this, tree sample based like JBoost model. I didn't try the CNN, but what I did try is I tried a different model, which I use actually the time series, the time series data of the time series data I collected. I ran a long short-term memory model, which is also another deep learning model, but that doesn't give me a huge improvement of the model accuracy. Probably because my data set is small. Yeah, so I would say yes. I would say the answer is yeah, probably yes. But I haven't tried yet. Also from if you see from the feature importance, NDVI is the most important one, and maybe B2, B5, and B8. B2, B5, and B8 may be important band values. Yeah. So just like I finish up, so kind of instead of I'm continuing with my script to wrap it up. So instead of having one records for 1 point from a single time point, which is from a single image, you can also do this time series, and then I think in the end I kind of put all the records here, so you have like separate CSV files, and you can read them in, or just like dictionaries or whatever, and then run your time series models, or yeah. So is the end of my workshop. So I'm happy to take questions if there are any. But thank you, everyone.
Thank you, Fei. I think based on what somebody also asked about the CNN model, I know you have used XGBoost for the demo here. Did you try with any other types, or was like in all the models that you tried, was it like XGBoost in the basic machine learning models? Did that give the best performance? Any
It doesn't give me the best performance for XGBoost. Like I said before, I do try the like long short-term memory model, which actually pretty common in the literature, like in other land use classification maps, classification models. But I didn't get much success with more complex the models. That's why I'm thinking, if the performance is equally poor, why not go with simple models? But I did try random forest, which like not as good as XGBoost. So yeah.
Okay, thank you.
Can you talk about some of the applications of this data and what you can do with these models?
Yeah, actually, one applications is our whole goal is to help farmers to deal with biotic and abiotic stressors. One biotic stressors is the four armyworm model, which is a pest, very prevalent in almost all maize field in Kenya, which is like a worm which eating up who is eating up the maize leaves. That's why if we know, the one application is if we know where the vegetation, where the cropland is, and we also know almost 90% of the farms in Kenya planting maize and other crops. So we want to like inform the farms in the region, like, oh, we kind of know you are having cropland and you have farms, and based on the remote sensing data, all your neighbors also have farms and maize. So it is very likely that the four armyworm will transfer from your neighbor's farm to your farm, and please be prepared for this four armyworm attack. And this is kind of we want to, by knowing where the farms is, we can know where the pest is, and we can know where we should get more control and get more civilians team on. Kind of that is our biggest hope out of it, and kind of not only for the pest alert. If we know you have maize, and maybe in a more advanced version of this model, we will relatively get to know when you plant your maize by analysis NDVI or NPP, which is a net primary productivity. We can also know your planting date of the maize. Then we have more information to tell you regarding to, oh, this is the early stage of your maize you just planted, which is more vulnerable to X attack. And when you move to the middle developed stage of your maize plant, you may be vulnerable for Y attack, which is maybe a totally different pest. And also we can do this to inform in the earliest, you are reaching the late stage of your maize, you may need a lot of water, and we have estimation of how much water you need for a late stage maize. But from the rainfall forecasting, you're not getting enough rainfall. So kind of by knowing the location and the crop of the farm, we are able to tell much more information about pest and climate and water stress about the farm. Okay, Hope that answered your question.
Yeah, that was very interesting. Thank you.
Mhm. Oh, I see a question in the chart. Would the dimensional reduction, like principal component analysis, improve the results in XGBoost? Yeah, I think that's a very interesting question. I will definitely try. Yeah, I will definitely. Yeah, I will definitely try it. I didn't do this before. But I definitely would like to try it. And in addition to this, I would say just to get rid of some, get rid of one thing I most time do is to get rid of those non-important variables like B9, B12, and then just we don't need that many predictors and see how the model performs with less variables, and see how can we achieve the same or relatively same performance with less variables. But thank you for the question.
Hey, I had one. You were just talking about maize. So how do you classify a vegetation as maize or some other crop? How do you know it's maize or it's mangoes, or how do you do that?
Oh, that's actually a good question. How do I know the vegetation are of if it is a cropland? How do I know it is maize? It's based on our survey in Kenya. We have our own field workers on the ground doing the survey directly with farmers, and we also have partners which has a network of 500,000 farmers, and our partners send out the messages like text messages to ask them what is the what do you plant, and we found that 90% of the farms have maize, or at least maize with other crops, or dual crop or whatever. So that is a kind of relatively realistic estimation based on the survey data we have. But actually, we also, before doing this, we also try a different model which only focus on cropland, and we want to know, we want to use the same data to see whether we can tell a maize from other crops, or we can tell from different crops. So except maize, another common vegetation, or a vegetation that we are promoting is cassava. I will just show. Yeah, it's kind of a root plant. People eat their root, and then it's kind of more drought resistant. That's why we are promoting this in Kenya, to say, especially if you are not get enough rainfall, please consider cassava instead of maize. And we have actually accurate, we have actually field data to field survey on the cassava field and the maize field, and of course there are some other minor crops like pumpkins or other vegetations and beans. Sometimes it's sunflowers, stuff like this. But maize, beans, and cassavas are the major crops we have. So I actually trained, I'm not showing here, but I actually trained a model to see whether we are using this Sentinel data to differentiate maize from maize, beans, and cassavas. But kind of in the end, that model doesn't work well. It's kind of really hard to differentiate those. First we have to deal with even though each maize variety, even though they're all maize field, they have different planting date, and a lot of times those planting date are not very accurate. They are based on the estimation from the farms. So, for example, what I really want to know is, for example, I really want to know the date of maize becoming mature. So I can know the data. So I can know, which images I should looking for, because for these images I need a date, which is really hard to get. And also, and the second is we really have an unbalanced class because those are the field survey data. So we have a lot of maize, but only several cassava fields and several other bean fields. So we don't have a balanced class data set to start with. And the third, I guess we have to admit, is it is very difficult to tell a maize from cassavas, or to tell one crop from another crop from space, from thousands of miles above the ground. But there are some, maybe I can share the link later, but there are some interesting, there's some interesting work along the line. I think I forgot the name of the institution. They once hold like a coding competition, which they provide the participants with our field survey data, and then ask them to team up and see what's the best model they can have to predict maize, cassava, and other crops. But yeah, that's a very good question. In summary, it is very hard to predict one crop from another crop.
Would you be kind enough in sharing the link?
Okay, yeah, I can. If I can find it now, I can share it now. But yeah, let me try think about it. Okay. Sorry, is someone talking? Oh, I think I found the. I think that's the link about the competition I talk about. I think I think their code is online in the GitHub. Do we have other questions? If no, maybe Rama, we can wrap it up.